Good day, everyone. Welcome to Elementary Number Theory. This is Emelyn B. Bonto, your discussant for today. The topic assigned to me is about congruences and its some basic properties. Let us begin with the learning objectives. At the end of the discussion, the student should be able to define congruence modulo denoted by M, state the basic theorems of the modular congruence relation, and apply the basic theorems of the modular congruence relation. A congruence is nothing more than a statement about divisibility. The theory of congruences was introduced by Carl Friedrich Gauss in his Disquisitiones Arithmeticae. He contributed to the basic ideas of congruences and proved several theorems related to this theory. In the first chapter of Disquisitiones Arithmeticae, he explains that he was induced to adopt this symbol because of the close analogy with algebraic equality. According to him, if a number n measures the difference between two numbers a and b, then a and b are said to be congruent with respect to n, if not incongruent. Putting this into the form of a definition, we have let m be a positive integer. Then an integer a is congruent to an integer b modulo m if m divides a minus b. In other words, if m is a positive integer and m divides a minus b, then we say that a is congruent to b modulo m. And in symbol, write a is congruent to b mod m, where m is the modulus of the congruence relation. If a is not congruent to b modulo m, then a is incongruent to b modulo m. Then write a is incongruent to b mod m. Here are some examples. Since 6 divides 37 minus 7, or 6 divides 30, 37 is congruent to 7 modulo 6. Likewise, 5 divides 48 minus 13, or 5 divides 35. So, 48 is congruent to 13 modulo 5. Also, 27 is congruent to negative 5 modulo 16 because 16 divides 27 minus negative 5, or 16 divides 32. But 22 is incongruent to 4 modulo 7 since 7 cannot divide 22 minus 4, or 7 cannot divide 18. Likewise, 19 is incongruent to negative 7 modulo 6 because 6 cannot divide 19 minus negative 7, or 6 cannot divide 26. Congruence is a generalized form of equality. Many properties of equality are being carried over to congruences. In the next theorem, like equality between two numbers, we see that congruence satisfies the properties of an equivalence relation. Theorem 1 states that A is congruent to B modulo M if and only if A is equal to B plus K times M for some integer K. For our proof, suppose A is congruent to B modulo M. Then, M divides A minus B, so A minus B equals K times M for some integer k, that is, by addition property of equality, a equals b plus k times m. Conversely, suppose a equals b plus k times m for some integer k. Then, a minus b equals k times m, so m divides a minus b, and consequently, a is congruent to b modulo m. For example, 37 is congruent to 2 modulo 5 can also be expressed as 37 equals 2 plus 7 times 5. On the other hand, 58 equals negative 5 plus 9 times 7. So, 58 is congruent to negative 5 modulo 7. Now the following are equivalent to each other and may be used interchangeably. A is congruent to B modulo M, or M divides A minus B, or A equals B plus K times M. Theorem number 2. Given any integers a, b, and c, and any positive integers m, the following hold. First, a is congruent to a modulo m. For our proof, the relation is reflexive since m divides a minus a equals 0. So, for reflexivity, on division by m, any number leaves the same remainder as itself. Next, if a is congruent to b modulo m, then b is congruent to a modulo m. For our proof, if a is congruent to b modulo m, then m divides a minus b. Hence, there is an integer k such that k times m equals a minus b. This shows that negative k times m equals b minus a, so that m divides b minus a. It follows that b is congruent to a modulo m, and so the relation is symmetric. So for symmetry, if a leaves the same remainder as b, then b leaves the same remainder as a. Next, if a is congruent to b modulo m and b is congruent to c modulo m, then a is congruent to c modulo m. For our proof, if m divides a minus b and m divides b minus c, then m divides a minus c. Thus, a is congruent to c modulo m, and so the relation is transitive. So here for transitivity, assume that a leaves the same remainder as b on division by m, and that b leaves the same remainder as c, then all three leave the same remainder as each other, and in particular, a leaves the same remainder as c. Next, if a is congruent to b modulo m and c is congruent to d modulo m, then a plus c is congruent to b plus d modulo m, and a times c is congruent to b times d modulo m. For our proof, since a minus c equals a plus quantity negative c, it suffices to prove only the addition case. By assumption, m divides a minus b and m divides c minus d. By linearity of the divides relation, m divides the quantity a minus b plus quantity c minus d. That is, M divides quantity A plus C minus quantity B plus D. Hence, A plus C is congruent to B plus D modulo M. Next, if A is congruent to B modulo M, then A plus or minus C is congruent to B plus or minus C modulo M, and A times C is congruent to B times C modulo M. Example, 19 is congruent to 3 modulo 8, then 19 plus 7 is congruent to 3 plus 7 modulo 8, or 26 is congruent to 10 modulo 8. Next, 19 minus 4 is congruent to 3 minus 4 modulo 8, or 15 is congruent to negative 1 modulo 8. And last one, 19 is congruent to 3 modulo 8, then 19 times 2 is congruent to 3 times 2 modulo 8, or 38 is congruent to 6 modulo 8. These facts might be right now a little strange, but the idea is simple. If we have a true congruence and we add, subtract, or multiply the same thing to both sides, the result is still true congruence. Now, what happens when both sides of a congruence are divided by an integer? Consider the following example. We have 14 equals 7 times 2 is congruent to 4 times 2 equals 8 modulo 6. But we cannot cancel the common factor of 2 because 7 is incongruent to 4 modulo 6. Since 6 cannot divide 7 minus 4, or 6 cannot divide 3. So this example shows that it is not necessarily true that we preserve a congruence when we divide both sides by an integer. Last one, if A is congruent to B modulo M, then A raised to n is congruent to B raised to n modulo M for any positive integer n. For our proof, we prove this by induction on n. If n equals 1, the result is true by the assumption that A is congruent to B modulo M. Assume that the result holds for n equals 1 up to k. Then we have A raised to k is congruent to B raised to k modulo M. This, together with A is congruent to B modulo M, using the property A times C is congruent to B times D modulo M, gives that A times A raised to k is congruent to B times B raised to k modulo M. Hence, by multiplication rule of exponent, we have A raised to k plus 1 is congruent to B raised to k plus 1 modulo M, and the result holds in the n equals k plus 1 case. So the result holds for all n greater than or equal to 1, or for any positive integer n by induction.